let's review the unit circle definition of trig functions a little bit. Right over here, I've drawn a unit circle, and when we say unit circle, we're talking about a circle with radius 1. So for example, this point right over here is the point 1, comma 0, x is equal to 1, y is 0. This point is the point 0, comma 1. This is the point negative 1, comma 0, and this is the point 0, comma negative 1. That the radius over here, the distance from the center of the circle, which is at the origin, to any point in the circle, or any point on the circle, I should say, this radius is equal to 1. So the unit circle definition of trig function leverages this unit circle. That's why it's called a unit circle definition. And we saw that if we define an angle as the kind of bottom side of the angle being along the positive x-axis, and then the other side of that angle, thinking about where it intersects the unit circle, so let's say that this is the angle theta, we define sine of theta and cosine of theta, or cosine theta and sine of theta, as the x and y coordinates of this point at which this side of the angle, this is the side that is not the positive x-axis, where that intersects the unit circle. So for example, this point right over here, if we would call this the x-coordinate of this point, so this value right over here, we would call that cosine of theta. We would call that cosine of theta. And the y-coordinate of that point, which is this point right over here, we would call that sine of theta. In the previous videos on the unit circle, we've talked about why this is really just a natural extension of the SOHCAHTOA definition. What's useful is it starts to work for negative angles, it works for angles, it even works for 90-degree angles, it works for angles more than 90 degrees, it works for angles less than 90 degrees. So it's really, really, really useful. But what I want to do is leverage what we already know about the unit circle definition of trig functions to help prove the Pythagorean identity. It almost falls out of the fact that this point right over here is on a circle of radius 1. So what is the equation of a circle with radius 1 centered at the origin? Well, the equation of that is x squared. We have other videos where we really prove this using the distance formula, which is really just an application of the Pythagorean theorem. The equation of a circle, of a unit circle, centered at the origin is x squared plus y squared is equal to 1, is equal to the radius squared. This distance right over here is equal to 1. Well, we've already said that we're defining cosine of theta as the x-coordinate of this point, and we're defining sine of theta as the y-coordinate of this point, and this point is sitting on the circle. It has to satisfy this relationship right over here. So that means, well, if we're defining cosine of theta to be the x, to be this x value, sine of theta to be the y value, and it has to satisfy this relationship, that means that cosine of theta squared plus sine squared of theta plus sine squared of theta needs to be equal to 1. Sine squared theta plus cosine squared of theta needs to be equal to 1. And that's just from the point. This is the x. Cosine theta is the x-coordinate. Sine theta is the y-coordinate. They have to satisfy this relationship which defines a circle. So cosine squared theta plus sine squared theta is 1. Now, this is called, as we've seen in other videos, this is called the Pythagorean identity. You say, why is that useful? Well, using this, if you know sine of theta, you can figure out what cosine of theta is going to be, or vice versa. And if you know one of cosine of theta, and then you can, or say you know cosine theta, then you use this to figure out sine of theta, then you can figure out tangent of theta, because tangent of theta is just...
All right, so we're going to stop there. Sorry, I made you endure 4 minutes, not 3. All right, so a couple things that I want to point out. So again, I know that he might not be the most animated. I think it's nice to see people's faces in videos, but a lot of times it's hard to do that with math. So I think, what's equation of this? What equation is this again? The equation of a circle, right? Centered at the origin with a radius of 1. So x squared, the fact that it's not being moved left or right, y squared, it's not being moved left or right, that means it's centered at the origin. And then the fact that this is 1 squared is the radius of 1. Okay, so this is the equation of a circle. All he did was take these coordinate points, cosine, comma, sine, because that's what we say for x and y, and he plugged them in for x and y. So he got cosine squared plus sine squared equals 1. What did he call this? Starts with a P? Pythagorean identity. Raise your hand. Does that look familiar from last year? Maybe, maybe not. Okay, good. This is key, like central, super, super, super important to what we're going to be doing for like almost the rest of the semester. This is going to be super, super, super important. I have no, I don't even know what word to use besides that. That's the only word I can use. So, it stems from the Pythagorean theorem, yes. So here's the cool thing about this. The cool thing about this is that you can either get it from the equation of a circle, right? So you can use the equation of a circle. You can also just use the Pythagorean theorem, understanding that this is sine and this is cosine. So cosine squared plus sine squared equals 1. That would be the Pythagorean theorem. Or you can also use the distance formula, which is what the rest of his video goes on to do, but I'll pause there. So you could get it from the equation of a circle, from Pythagorean theorem, or from the distance formula, but all of them will equal this when you plug them in. Yes? It is yes, it is the Pythagorean theorem, but instead of using x's and y's, we use sines and cosines. Yeah. So here's what I want you guys to do. On your blue piece of paper, all right, I really don't care where you write it. I really don't care how you decorate it, if you want to label it something at the top, but I want you guys to call this the Pythagorean Identities. There's 3 of them, by the way. This is only the first one. But call these the Pythagorean Identities and write this one down, but be careful, because I'm going to rewrite it in a different way, because it's not usually seen in this way. So write it like this instead. These are called the Pythagorean Identities. The word, yeah. Pythagorean identities. And then, Scott, would you turn the light back on for me? Thank you. All right. So the first one that we just talked about, normally when you actually discover it for the first time, it looks like cosine squared plus sine squared because the x's we normally put first. But when we actually write the first one, we actually write it as sine squared theta plus cosine squared theta equals 1. Now, have you ever seen this notation before, sine squared theta? Some people in my, even in calculus, you know, if you don't have somebody that actually sits here and spells it out for you, sometimes it's hard to know what you're talking about. So this, I'm going to rewrite it in a different way, is the exact same thing as this. These are one and the same. Just a different notation. You remember yesterday how we were talking about notations? So we wrote arc sine is the same thing as sine inverse. We wrote that yesterday at the very end of our lesson, correct? Yeah. All right, beautiful. So again, these are one and the same thing. Sine squared theta plus cosine squared theta can be written in either of these ways. But 99.9999999% of the time, you're going to see it written like it is in purple. Why do you think that is? Why do you think we would write it more often in purple than and we see in red? Yeah, you don't have to write parentheses, that's kind of nice, and you just write the two in a different place, and they mean the exact same thing. So we're just trying to simplify our work rather than making it more complicated, so that's why we write it in purple. So anytime you see anything where the 2 is like after the sine but before the theta, it just means sine squared theta. And it implies the same thing as the second one does. All right. So there's 2 other Pythagorean identities, but they stem from this one. So let's see if we can figure them out through discovery. So I actually want you guys in your notebooks. You guys are just going to do some scratch work, because I don't want you to put scratch work on this blue paper. This blue paper is only for final work. So in your notebooks, I want you guys to do some scratch work. So how about this? Anything that I want you to put on your blue paper, I'll highlight like that. Anything that's scratch work, I will not highlight. So if it's highlighted, put it in your notebook. I'm sorry, if it's highlighted, put it on your blue paper. If it's not highlighted, put it in your notebook. All right, so let's discover the second one together. Sine squared plus cosine squared equals 1 is the first one. Here's how we get to the second one. And you guys can simplify this for me, and you guys can tell me what it equals. What if I divide everything by sine squared? Did I change the equation at all? Like, is it still equal to what I started with? Is that okay mathematically to divide everything by sine squared? Yeah, as long as you do it to one side, you can do it to the other side. So what I did is okay mathematically. I didn't make any changes to the equation necessarily. So in your groups right now, I want you guys to discuss what each of these fractions simplifies to if you can rewrite them in a different way. So talk about that for about 30 seconds with your groups. Let's start with the easier one. What is sine squared divided by sine squared? 1. Okay, good. This is just 1. I heard some people whispering that sine divided by cosine is tangent, but what's the reciprocal of that? What's cosine divided by sine? Cotangent. And notice that we still will keep it squared. So cosine squared theta divided by sine squared theta is cotangent squared theta.
Why would it be squared?
Why would it be squared? For the same reason that I can... So the question was, why would it be squared? I'm going to erase this really quick, so just look up here for me. Put your pens down. If I rewrite cosine squared over sine squared theta like this, cosine squared theta over, oops, sorry, my bad. Cosine theta over sine theta squared. Cosine over sine is cotangent, and squaring it makes it cotangent squared. All right, and then last but not least, what's 1 over sine squared theta? Cosecant squared theta. Cosecant squared theta. This is the second Pythagorean identity. It's highlighted. What does that mean you should do? Write it on your blue paper. That's the second Pythagorean identity. Now, good news. If you're good at memorizing, great. Memorize all 3 of them because we still have 1 more to learn. If you're not good at memorizing, was it pretty, it took us maybe a minute the first time, but now that you're familiar with it, was it pretty easy to get from the original one to this one? Yeah. All we had to do was divide by sine. No problem. Yeah, so now to find the third one, what do you think we're going to do for the third one? Divide by cosine. So go back to your scratch paper again. Take the original Pythagorean identity and divide everything by cosine and see what you get. So, shout it out for me. What's sine squared over cosine squared? Tangent squared theta. Good. Tangent squared theta. And what's cosine squared divided by cosine squared? 1. And what's 1 over cosine squared? Secant squared theta. So this is the third Pythagorean identity that you need to have written on your paper. Tangent squared theta plus 1 equals secant squared theta. Again, the reason I like these is because if you can memorize the first one, and memorize is even a strong word because I think if you know the unit circle already, that if you can just think about the Pythagorean theorem, that it's pretty easy to memorize, quote unquote. If you can know the first one, if you can memorize the first one, you can really easily figure out the other two just by dividing by sine or cosine. Now, why would these be helpful to us? Why are they important? Yeah, go ahead. Number 1, because when you see them, you know what it is. What else? Yeah, you can be able to figure out missing pieces of missing information. So, for example, now that we have our 3, does somebody have neat handwriting that I can take a picture of their 3? Now that we have our 3, here's the thing. Now that we have our 3, given any piece of information, sine, cosine, tangent, secant, cosecant, or cotangent, you can figure out information about other pieces. So if I give you information about sine, you can figure out cosine. Or if I give you information about cotangent, you can figure out information about cosecant. And you're able to find all 6 trig identities using these functions, whether or not it's in different procedures of doing it, but you can figure out all 6 by using these identities. We're going to be using these identities a lot. One of my favorite parts of trigonometry is when we get to solving equations and making equations match different sides. And so you might not know what that means yet, but we'll get there eventually. And these come up all the time when we do that. We have to use these. They're kind of like little puzzles that we solve, but these come up very, very often in those lessons. All right, we have one more thing to talk about today. So I'm going to put something up on the board, and I want you guys to write it down. You can put these on your blue paper as well. We're going to be writing down over the next few weeks a lot of rules, like little rules, and some of them will be things we use a lot, and other ones will be things we use every once in a while. So what I want you guys to do on your blue papers is I want you kind of to divide it up, so like section this off so that you know that these identities are different than what we're about to write. So whatever way is best for you to organize them is fine, but just make sure that they don't get confused with what we're about to write, because these are different identities. All right, so these are called the cofunction identities. Let me fast forward to these. There we go. So these 6, I'll highlight them so you know they're supposed to be on your blue paper. Do me a favor though, everywhere you see a 90 degrees, can you instead write what? Pi over 2. So write pi over 2 for all those, because I don't like degrees. I'm biased. My mind is in calculus most of the time. We don't talk about degrees in calculus. These are called the cofunction identities. So when you're writing it on your blue paper, the first ones were the Pythagorean identities. These are called the cofunction identities. So these ones I think are pretty obvious. They're pretty self-explanatory. So once you write them down, I'll talk a little bit more about them. But essentially all these say is that for every, like, sine goes with cosine, tangent goes with cotangent, secant goes with cosecant. But essentially they're called cofunction identities because complementary angles would be congruent with both of those. And I'll talk about what I mean by that in just a minute. So do you guys remember what complementary angles are back from, like, when you guys took some geometry stuff? What are complementary angles? Angles that do what? They complement each other. I like your dress. Say it again. They both add to 90. Yeah, supplementary angles add to 180. Complementary angles add to 90. So on your unit circle of your pink paper, I want you guys to look at, and we'll start with 30 degrees and 60 degrees. All right, so here's a unit circle. So here's 30 degrees and here's 60 degrees. All right, what is sine of 30 degrees? 1/2. Sine of 30 degrees is 1/2. The complementary angle with 30, or in other words, the angle that adds up to 90, would be 60. What's cosine of 60? Half. So that's essentially a summary of what you just wrote down. So if you look back at your first cofunction identity that you wrote down, you said sine of theta equals cosine of pi over 2 minus theta. So in other words, sine of 30 equals cosine of 60. Or cosine of 30 equals sine of 60. So pretty much essentially their coordinates just flip when you look at angles that add up to 90 degrees together. It also works with 45, by the way. Radical 2 over 2 is cosine of 45 degrees. What number adds to 45 to make 90? Another 45. So notice that sine and cosine are the same there as well. So all that it means is that two complementary angles, sine and cosine, will be the same of those complementary angles. Secant and cosecant will be the same of those complementary angles when you look at them. So this one is a minor identity. Okay, we will not use it very much. What did I say about the Pythagorean identities? We'll use those a lot. Okay. Okay? So these ones are nice to know. These ones I want you to have on your paper because as we go through, if we do need to use them, I want you to have them in one place. But these are a nice to know. The other ones are a need to know. Like very, very, very important. All right, beautiful. So here's what we're going to do. We are done with chapter 4. All done with chapter 4. We're not going to have another test on chapter 4 because we've only learned a few things after we took our last test. So these last few things I think actually go well with chapter 5 anyway. So we're actually going to kind of push them into chapter 5. So when you take a chapter 5 test, you guys will be tested on these things as well. So don't plan on taking a chapter 4 test again. We already kind of took that one that we did last week. Tomorrow, what's due tomorrow? Test corrections. We're also going to start 5.1 tomorrow. We're going to get a very brief introduction to it. So you guys can go ahead and pack up for right now, and then we'll talk about that later.